All right, thanks for that introduction, and what a treat to go after Michael, who just gave us a really nice primer on ozone chemistry in the presence of these devices. So my name is Victoria Barber. I am a postdoc at MIT. There's a couple of different contact emails up there for me. I'm moving to UCLA in 2 weeks, so if you want to get a hold of me, I advise using that new email. We also have a preprint out on this work. The QR code is up there, and I'll show it again later in the talk. Michael's already shown it as well. And I do want to mention this is a collaborative project between us at MIT and Jesse Kroll's group, this sort of array of graduate students who worked on this project with me, as well as some folks in Frank Koich's group at Harvard, and Manjula Kanagaratna, who's at Airdyne Research. All right, so what have we learned so far? So we know now from our talks yesterday that GUV222 is a skin and eye safe alternative to sort of more conventional wavelengths, and therefore can be really good for airborne pathogen transmission mitigation. And Michael has also just shown us very beautifully that GUV222 can make ozone. So what I'm really going to focus on in this talk is the downstream effects, which Michael has already kind of introduced us to. And there's reason to believe, as again, Michael has just shown us really nicely, that GUV222 may have additional effects on indoor air quality. And those additional effects include the production of additional oxidants, especially OH radicals, as well as when there are VOCs present, as there are in indoor environments, the production of oxygenated volatile organic compounds, OVOCs, and particulate matter as well. So we wanted to study these things experimentally, and so what we did was set up a chamber experiment. This is a much smaller chamber than they have at NIST. It's 150 liters. We have one of the Ushio Care 222 lamps mounted above the chamber. And what we're going to try and do is monitor the chemistry induced by this lamp in real time under these sort of idealized conditions. So I do want to emphasize that radiance in our chamber with the full intensity of that lamp is very high. It's around, the UV fluence is around 45 microwatts per centimeter squared. So we know that's not a realistic irradiance, right? We're just trying to come up with conditions where we can measure the chemistry and get a sense of how well we actually understand the chemistry that's going on. And then we're also going to use a box model, which uses this very old chemistry that we understand really well to get a sense of how well we can predict the chemistry that we're seeing in that chamber. And we're going to measure in real time with this suite of analytical instruments. So we have ozone, we have a couple of mass specs that show us VOCs and OVOCs. We have some particle phase measurements as well. And we're going to do this under a range of conditions. So we look at several different VOCs under a couple different concentrations. We look at different humidities, and we attenuate the lamp. We do a dark ozone analysis experiment. We do one with the lamp at a factor of 5 lower intensity and one at this full intensity of the lamp. All right, and I'm only going to talk about this very briefly because Michael has already done a really nice job, but we do indeed see ozone forming. And as Michael said, our ozone production rates are in good agreement with those other measurements as well. The steady state ozone changes with the ventilation rate in the chamber, as you would expect. And we also do a pretty simple model of this using, again, that known ozone photochemistry and a much rougher estimate of the UV fluence in our chamber with like very simple sort of geometric calculations. And we get really good agreement. I think this is possibly a coincidence, but it does say that our UV fluence estimate is a decent one. But what I really want to focus on is what we did next. So at this point, we started adding in some VOCs to the chamber. The data I'm showing here is for cyclohexene. That's this cyclic alkene you see here. And so it's very simple, right? We introduce this VOC into the chamber and we see it decay away in the presence of the lamp. And so cyclohexene does react with ozone, but we know how fast that reaction should happen. And so what we can do is we can draw out, okay, if it was only reacting with ozone, here's the decay that we would expect to see. The decay that we're actually seeing is much faster than that. And so we call this the excess reactivity. And we can quantify that excess reactivity by fitting that decay. And when we do that, we're able to get out a number for that excess reactivity. And what we find is that it's consistent with the presence of OH radicals, so this additional oxidant that can be causing this oxidation reaction that's removing this VOC and making byproducts. So let's talk a little bit more about those OH radicals. So Michael's already shown us some of these reactions. So again, ozone plus light, it photolyzes, you get O2 and this excited state oxygen atom, which then reacts with water to make OH radicals. And just as a note, OH radicals can also form directly from the reaction of alkene and ozones as well. And again, this is all old chemistry. I really liked that Michael put it that way. This is something we atmospheric chemists have understood for a very long time. So what we did was we did these experiments over this wide range of reactivity conditions. We did those fits and we extracted a number for what we thought the OH concentration was in those experiments. And then we compared with our box model. And we found that across this pretty wide range of reaction conditions, we get very good agreement between the models and the measurements. And so what this tells us is A, that excess reactivity is indeed due to OH radicals, and B, that we understand very well the chemistry that's producing and consuming those OH radicals. And we also have some product data that supports this as well. Just for time, I'm not going to show it today, but that is in the preprint, and that's that QR code one more time. All right, so we've seen ozone, we've seen OH, we have VOCs, so we should also be seeing some OVOC products forming. And indeed we do. So this is a mass spectrum. This is from one of our chemical ionization mass spectrometers. So this one in particular is looking at OVOCs specifically. And this is a mass spectrum that's taken 30 minutes after we turn the lights on, and it's background subtracted. So everything that you're seeing here is a product, something that's growing in. Now, this is not calibrated, so we don't really know like what the concentrations are of those products, but this is just to say there's a lot of chemistry going on, there's a lot of OVOCs forming, and everything that's in blue in this spectrum, this is something that has 6 carbon atoms in it. So we started with a 6 carbon species, we're coming out with a lot of 6 carbon species. It just shows there's a connection between the products and the reactant. Interestingly, we also see that the products are different from a dark ozonolysis experiment. So if it was just the ozone that was reacting, right, you would expect that if you didn't have the light and you just put in an equivalent amount of ozone, then the products that you would see would be exactly the same. But that's not what we see. We see that the ratios of products are different. We see different things on different mass channels. And the reason for that, we think, is that there's OH. So OH is causing additional chemistry that's leading to different products than ozone alone. And if we look into the molecular formulas of these products, which again, I'm not going to show in detail today because things get very complicated very fast, what we do find is that the products that we're seeing are consistent with both ozonolysis reactions and OH chemistry. And so this tells us that we're having OH-initiated oxidation in addition to that ozone chemistry. The last thing I want to show you is that we do see organic aerosol formation. So this is data for 3 different VOCs, cyclohexene, hexanal, which is a VOC that only reacts with OH radicals, and limonene at 100 ppb, starting concentrations in our chamber. And in each of these cases, we see some organic aerosol forming. Now, I won't go too much into kind of the quantification of this and what it means for indoor air, because again, our UV fluences are very high. The concentrations, these VOCs are maybe not representative, just to say, you know, we do see aerosol form. All right, so what we have at this point is these measurements that show us that we're making OH, we're making ozone, we're seeing OVOCs forming, we're seeing particles forming as well. And we also have this box model, and we like that because our box model is agreeing really well with the chemistry that we've observed in our chamber. So that tells us that we understand that chemistry pretty well. And what we're going to do now is take that validated model and start trying to apply it to some more realistic sort of scenarios. And so what we've done is to run that model, again, using all this known chemistry for sort of a range of light intensities ranging from 0 to sort of very reasonable light intensities to the really, really high UV fluence that we had in our chamber. And also for a range of ventilation rates spanning, very low ventilation that you might see in like an older home to a high ventilation rate you might see in like a healthcare setting. And we do this for sort of a variety of parameters. So these plots, if you go to our paper, there are, I think, 4 of them in the main text and then maybe another 10 in the SI. So it's really a rich area to dig into. But the ones I'm going to show here are just for the ozone and oxidation products. And what we find is really kind of 2 main conclusions. The first is that 222 light, UV222, cannot be a substitute for ventilation, because at very low ventilation rates, what you find is the buildup of these oxidation products, the buildup of ozone, and so on and so forth. And so what this means is that even if you are doing a really nice job of disinfecting the air, you've essentially exchanged one problem for another. The second is that keeping the UV fluence levels as low as possible. So the lowest value that you can manage that still gives you a good effective air changes per hour as far as disinfection is really what we want to be targeting, because that will allow us to mitigate some of those downsides, some of these indoor air quality impacts. So I'm going to wrap up there and just remind you what we've done. So we've done these chamber experiments that show evidence of a bunch of secondary species forming. We see ozone just like everybody else. We also see evidence of OH radicals, of OVOCs, and of organic aerosol from this 222 nanometer induced chemistry. And the resulting concentrations of these species in our models, we showed that these can be really high, much higher than you might usually find in an indoor environment without these lights, something we need to consider when we're thinking about sort of the UV fluence levels that we're trying to achieve with these lamps and how we're going to integrate them with existing ventilation systems. And then these kind of two main conclusions that I showed you on the last slide. The first is that GV222 cannot be a substitute for ventilation. And the second is that keeping those fluence levels as low as possible is really critical for mitigating the detrimental effects on indoor air. All right, so this is my acknowledgement slide. All these folks at MIT, in particular on the model slide, I chatted at Matthew and Lexi. They really built and ran that model. It's fully their work. They deserve recognition for it. Frank and Yahweh helped us with some of the instrumentation, data analysis, and then Module as well for some instrumentation on this project. So thanks so much for your time, and I'll be happy to take any questions.
Thanks for a great presentation. Singlet oxygen is also known to be a very powerful oxidant. How do you know it doesn't interact directly with the VOCs to make secondary products, that's not a viable kinetic mechanism?
Yeah, it's a good question. Early on in the project, we did some modeling, and essentially just the reaction with oxygen from a kinetic perspective is going to overwhelm
it. Thank you for your excellent talk. I have a question about your enclosure. You said that the volume is 150 liters. Would you care to make any other statements about it? Is it transparent to visible light, for example?
Oh yeah, it's made of Teflon. So it is transparent to visible light. It's fairly UV transparent. We did some I would say very rough measurements of the transmission of the UV into it, and we didn't see much in the way of attenuation, but I think it's possible that we're losing some light on the way in, and then also probably some of the light is bouncing around in there, which is kind of canceling those errors when we do our modeling.
Okay, so you say it's made of Teflon.
Yes.
Then it's not transparent to visible light, then, if it's more than a few millimeters thick.
It is not more than a few millimeters thick. It's a Teflon film.
Ah, it's a Teflon film. Very good.
Yeah.
The reason for bringing this up is I think this is also relevant to the studies presented by the last speaker. We've only talked about the absorption spectrum of ozone that peaks at 254 nanometers, but it's well known that there is a second absorption band of ozone that peaks in the visible, in the orange, at about 600 nanometers. The peak absorption cross-section is weaker, but the bandwidth is enormous. So in a real scenario where we have a home or a business with interior lighting, the intensity of visible light and its bandwidth would also have a tremendous impact, I believe, on the photodissociation of ozone. So I just thought I would mention that as something to be we might want to consider.
Yeah, it's a good point. I think there are probably people in this room who can speak a little bit more on that than I can, but I will say that my understanding is that OH concentrations in indoor environments have been investigated fairly extensively and are quite low, which suggests that the visible light photolysis of ozone in indoor environments is not a huge issue compared to this UV photolysis.
Okay, it's time. Thank you for a great talk.